This digital learning resource is going to teach you about thermodynamics, a huge Q, heat. We're going to start with talking about heat and thermal energy. These are the two important concepts. And remember, heat only exists when there is a transfer of energy. And remember the hot nickel ball? When it's in contact with ice, it stops when it reaches thermal equilibrium. The most important equation about heat that you'll need to use all the time is Q equals to mc delta T. And the other really important equation, Q system equals to negative Q surrounding, which also should be easy to understand because it is just about conservation of energy, hinting semester 1. And we used both these two equations in the first experiment to determine the identity of the mystery metal by its specific heat capacity, which is the C in Q equals to mc delta T. So what happens when heat goes into a system, which is endothermic? Either the increasing kinetic energy, which is the increasing temperature, using the equation Q equals to mc delta T, or the increasing potential energy, which is phase change, using the equation Q equals to mLF and Q equals to mLV. It is an either-or situation, and exothermic, when heat leaves the system, is just the opposite, decrease of temperature or change phase of freezing and condensing. We can prove this either-or situation in the immersion heater lab when heat goes into the system. This is the graph we made, but it is easier to see on the graph from the book. When the phase is changing, temperature does not change, and the other way around. So it is always an either-or situation. Calorimetry is a technique that we use in almost every lab. In all of the 3 labs, and you can see from the calculated data of the 3rd lab, they all circle around the 2 equations I mentioned. Q equals to mc delta T and Q system equals to negative Q surrounding. And then going back to the idea when heat changed the potential energy in the system. We use LF and LV to calculate the heat, which is the latent heat of fusion and vaporization. And this is the physicist way of talking about it. And now change to the perspective of a chemist using entropy, delta H. So remember, the entropy is only about the potential energy in the system, breaking and forming bonds. And positive entropy causes decreasing temperature in the surroundings. Negative entropy causes increasing temperature in the surroundings because of the heat released when forming bonds. And combustion reactions are always exothermic. And note that it is only about the compounds with 2 or more elements in the Hess law. The last part, spontaneity. There are 2 driving forces that will cause the reaction to happen, enthalpy and entropy. We just talked about enthalpy. So since reactions happen to become more stable and less potential energy means more stability, so negative delta H, exothermic, is more likely to happen. Entropy is disorder or number of microstates. Based on the second law of thermodynamics, positive entropy that increase temperature to increase disorder in the system is more likely to happen. So based on those, how do we determine if a reaction will happen or not? We use Gibbs free energy law. When both enthalpy and entropy are favorable, G is negative. When both are unfavorable, G is positive. So a negative G means that reaction would happen, and then positive G means that it won't happen, which is non-spontaneous. Just like on this graph, the reactions that fall on the second coordinate always happen. The ones falling in the fourth derivative won't happen unless forced, such as photosynthesis. And the first and third coordinates are a little bit trickier. They need to be above or below the threshold temperature in order to get G to be negative, which will make the reaction spontaneous.
That's all for thermodynamics, and thank you for watching.